Okay, so now you've had a bit of a think about what factors you think are going to impact conduction. So when we write down the equation for conduction, what we're trying to calculate is the power, which is the rate of heat transfer. So power is equal to the heat, which is given the symbol Q, over the change in time, so the length of time it's got to transfer. So Q divided by delta T. Now, when you were considering what would impact it and what would increase this rate of transfer, hopefully when you came to surface area, you realized that a larger surface area would increase the rate of heat transfer. So intuitively, you probably know this because on a very cold night, you probably curl up into a little ball, which decreases your total surface area and so decreases the rate that you're losing heat. Now, it's inversely proportional to the thickness of material. So on a very cold day, you'll put on lots of layers of clothes to increase this thickness and decrease the rate of heat transfer. It's also proportional to the temperature difference between the two sides. If we have a really hot side and a really cold side, then heat will transfer very quickly. So on a very cold day, your very hot coffee will lose heat very quickly. If, on the other difference, you don't have such a big temperature difference, if you have a tepid cup of coffee, which means a not too hot cup of coffee, on a warmish day, then the rate of heat loss is going to be much lower. And so intuitively, we know that the rate of heat transfer is proportional to the surface area times the change in temperature divided by the thickness. So we can write this as a equation. P is equal to K. Now K is this proportionality constant. So it actually depends on the type of material. So some things will have high proportionality constant, so a good thermal conductivity, such as metals, and other things like asbestos, poor conductors of heat, and so K will be low, times A, and then we've got the temperature difference between the two sides. It can be large or small, so this D is equivalent to this delta. D just generally means smaller, but it can be either, and D on the bottom means the thickness, so that's the difference in the X coordinates between the two sides. Again, it can be big or small. And so this is our equation for heat transfer through conduction. So these absolute value signs are just because the direction is always given from the hot side to the cold side. Heat always transfers that way. So we always give a positive number for the rate of heat transfer. So what we have here is a table showing this thermal conductivity constant, the K, in watts per meter per degree C, which is the same as watts per meter per Kelvin, for some different materials. So you can see the metals up here are relatively high. Of interest, as we'll see in a demonstration in a minute, aluminium's 238, copper 397, brass is written over here as 109, and iron, which is the main component of stainless steel, is 79.5. Now, non-metals generally are lower. So asbestos, which we've discussed briefly, is 0.08. Now, an exception to that is diamond, which is actually really high. It's a really good conductor of heat with 2,300. And water is down here at 0.6. Wood also fairly low, like asbestos, 0.08. So that's a good thermal insulator. So gases also tend to be good insulators. You'll often leave an air gap if you want some form of insulation. So air is 0.0234. Okay, let's have a look at the demonstration now. What we're going to look at now is a demonstration showing the different thermal conductivities of different metals. So what we have here is aluminium with the red flags attached. So the thermal conductivity of aluminium is 238 watts per meter per Kelvin. Here we have brass with a thermal conductivity of 109 watts per meter per Kelvin.
Here we've got copper with a thermal conductivity of 397 watts per meter per Kelvin, and here's stainless steel with a thermal conductivity of 79.5 watts per meter per Kelvin. Now what I'm going to do in a minute is light this Bunsen burner, which will provide heat to this metal plate, which will be conducted along each of these different metal arms. Now I want you to think about is on which of these arms are the flags going to drop off first. The flags are connected by little globs of wax. When that wax is melted due to the heat, the flags will drop off. So let's light the Bunsen burner now.
And now, before we proceed further with this demonstration, I want you to make a prediction about which coloured flags are going to drop first.